In today's lesson, we're going to be using light to measure objects in the universe. And so the question that I have for you is if humans have never directly measured another celestial body, now farther than the moon. So the question becomes, what does that mean? Directly means going there and actually being on the surface and collecting information, people doing that. And celestial is a new word that we'll be talking about a lot about in astronomy. That just means objects beyond the Earth's atmosphere. So we haven't been any other place but the moon, yet we have so much scientific data about the night sky. So how is that possible? How does that occur? And today we're going to learn how we can use light to help us learn more about these distant objects. So yesterday we talked about the electromagnetic spectrum. The spectrum is all of the different types of electromagnetic energy arranged by wavelengths. We know that gamma had the smallest wavelength, the highest frequency, and had the most energy, all the way down through to radio waves, which have the longest wavelength, the lowest frequency, and the least amount of energy associated with them. And it's this that makes it possible for scientists to view the night sky and see images like this and like this. So scientists have learned to use the atomic spectras to help them determine these compositions of these distant objects. And they have learned that every element from the periodic table has its own unique fingerprint of light, and they've been able to use this to help them determine not only that composition, but temperature and speed and some other things. So what I would like to do is I'd like to show you a small clip of how to use these and kind of give you an idea of what's going on, and then we'll continue our notes on this.
If you use a prism to spread out white light, you will see a continuous spectrum of colors. If you first pass the light through a cool gas, you will see dark lines, or gaps, in the spectrum. This is called an absorption spectrum, because the dark lines are created when the cool gas absorbs the specific colors from the light passing through. If you heat up this gas until it starts to glow, it will produce an emission spectrum, bright lines of color in exactly the same place as the dark lines in the absorption spectrum. These lines are the specific colors this gas emits when heated. Every element produces a unique set of lines, thereby making it possible to identify elements by looking at spectra. Thus, we can discover what the sun and other stars are made of by looking at the lines in their spectra. By seeing these lines, we can figure out these distant objects' temperature, speed, distance, and age, among other things.
So the first type of spectra that you just saw in that video was called the absorption spectra. And it was talking about when light passes through a cooler gas. And you have the continuous spectrum, is what it's called, is continuous rainbow. Like if you were to take a prism to break up the white light from the sun that shines in the window, you'd get this nice rainbow. But you'll see missing spots of wavelengths of color that indicate a particular element that's in the star. And that's how helium was found when they were determining that. The second type of spectrum that you guys saw in the short video clip was what we call an emission spectra, or a bright line spectra. And what this is when you have gas that's illuminated, which we're going to be doing in lab, or you have already done in lab, you're going to look at tubes that have a particular element of a gas inside, and I'm going to turn it on like a light bulb, and it's going to illuminate, and you're going to be able to use a spectroscope to determine and look at the different bright line spectras. But here's some great examples of this for you. At the very top, here's an example of a continuous spectrum that you guys will see when you look outside at the sun. And then here is some other ones. And here's hydrogen down below. You can see the colors of the different wavelengths that represent helium, hydrogen above, and then mercury, and then sodium. So here's some more examples of what we will be doing in lab. So we're going to look at something similar to this, and we're going to hold up a spectroscope so that we can see the bright lines spectra for those particular elements that are in the gas state. Here's a great example of how we can see the different things. We're going to be looking at the sun through, not a prism, but we call a spectroscope that will show us the continuous spectrum. And then I'm going to turn off the lights, and we're going to look at the hot gases that are inside of this little, looks like a light bulb light socket. And when we hold the spectroscope, we'll see the bright line or emission spectra. We won't see any of the absorption spectras, but we will be interpreting those in a little bit and trying to determine the composition of certain distant objects using the absorption spectra along with the bright line spectra. So here's an example that I would like to show you before you go forth and do this in your packet on page 13. So how you would determine a star's composition. So for here you see the star spectrum. We want to know what is the composition, what is in the star. So we have 4 different emission spectra by 4 different elements: lithium, hydrogen, helium, and sodium. So the question is, which of these is in our star? And so how you start to do this is you need to start lining up the bright line to the corresponding light line that's in the absorption spectrum. So if I could make a little line here, I would start to see that if I look at this line down to here, they match up. But I have to be sure that each line in helium matches up to a corresponding line below. And if I do that, I will see that all of them do. So I can say that helium is in the star's composition. Now if you look, you'll see some leftover lines. Here's 1, 2, 3, and 4. And so there's another element in there, and which one is it? So if I go and I look further, I will see right above this one, if I go straight up, I'll see this line. And I will see this line, and I can come down and see it corresponding. And you can do this in a minute in your packet with your pencil or pen. You can do this on top of the diagram that's there. So if you can see, I have matched up all of these lines with their corresponding ones. I know that hydrogen and helium are in this star. I do not see sodium and lithium are not in the star. And the main reason is I have these lines here, but do you notice how there's nothing down below in that corresponding star spectrum? And same with here in sodium, you have some other lines that don't match up. That is your indication that these 2 elements are not in the star's composition. And this star's composition is helium and hydrogen. So what I would like you to do is stop the video, and on page 13 I would like you to determine what is the composition of the unknown star that's at the very bottom of the diagram. You can use your pencil to match up the corresponding wavelengths, and I give you a hint, they're all not in there. So please do that. So a quick answers to your puzzle here that you had. The composition of that unknown star was Sr for strontium, Na for sodium, and Cd, which I think is cadmium. Those were the 3 elements that were in the unknown. If you wonder how to do this, make sure you stop the video and ask Mrs. Riley or I, depending on whose classroom you're in. But moving on, so we've determined how scientists can determine the composition of stars. The next question is what are they doing out there? Are they moving away? Are they moving towards? And how fast? And one of the ways that scientists determine that is what we call the Doppler effect. And so I'd like to take the time to explain what this is. So now that we know what spectral lines are, we know that each element has its own unique spectra. When they're determining these and looking at these of distant objects, they will notice that these wavelengths may be shifted to either the blue end of the spectrum or the red end of the spectrum. And that will tell an astronomer or a scientist that that object is either moving away from us on Earth or towards us. And here's a good picture here for you to look at. Here's a person seeing a distant star, and if those wavelengths of that star are shifted towards the red end of the spectrum, it tells you that it's moving away. And if they're moving towards, those lines shift towards the blue. So I will be showing you a short video clip on what is really the Doppler effect and how we can use that with light waves to determine this motion.
Most scientists believe that our universe is expanding. That belief is based on an interesting property of light waves called the Doppler effect. Here's how it works. All waves travel outward from a source. A stone dropped in a pond, for instance, will produce waves that move out in a circular pattern from the splash. Light works the same way. When a camera flashes, light waves move out from the flash bulb. When the source of a wave is stationary, the waves can be thought to form circles radiating out from the source. But when the source is moving, something very interesting happens. The waves ahead of the moving source are bunched closer together. The waves trailing behind the moving source are spread out.
We hear this effect when a moving car blows its horn as it passes us. We hear a high-pitched sound as the car approaches us because the motion of the car bunches the sound waves closer together. When the car passes us, we hear a distinct drop in pitch because sound waves are now spread out by the car.
Light waves show a similar shift. If a source of light, like a star or a galaxy, is moving toward us, the light waves are bunched together, and we see the light with a slight bluish tint. If the star or galaxy is moving away from us, the waves stretched out, and we see a reddish shift in the color. Because all galaxies show a red shift in the color of their light, this is evidence that they're moving away from one another. So the red shift is evidence that our universe is expanding.
So from the video that you just saw, here's some other examples to show you a train that's stationary, and then when it starts to move, the wavelengths in front of them get smushed together, indicating we will hear a higher pitch, and behind it they stretch out to hear a lower pitch or lower sound. Same with light waves, exhibit the same effect. So what does that look like when it comes to spectra? So we need to be able to recognize this. So here is a spectra of hydrogen with no motion. Here's the different colors. When this oxygen is on a star that is moving away from us, you can see how the lines are still spaced apart. They're still equidistant from each other from the above. However, all of them have shifted to the red end of the spectrum. And over here, this hydrogen is on a star that's moving away. All of them will shift towards the blue end of the spectrum. Again, here's an absorption spectra. Here, just take a look at these double lines in the center. Here they are at rest, but if it's moving towards you, you can see how they've all shifted a little bit towards the purple, and over here, if they're moving away, shifted towards the red. And the more they're shifted to that side, tells you that they are moving away. So if you would take a minute to answer this Regents Review question and tell me if you, if after looking at these two diagrams, the shifting of the spectral lines indicate that the star is doing what? What is the star doing? You look at the lines, you can see they're equidistant. They're all in the same spot, but they have shifted towards the red. And from our notes that we just did, when it's shifted towards the red, it is moving away. So our answer here is number 2, moving away. And this concludes our video on interpreting light, and we'll be continuing this in lab and in our homework.